All right, we're going to go over section 2.7, factoring special products. You'll notice this is the last section in the factoring section in chapter 2 in your guided notes book. So we're going to work through this. And then you're going to do some practice factoring all around, but specifically with these special cases. So let's talk about the special cases. Special cases are related to perfect squares. So I have a list of perfect squares here just as a reference if you need to look back at this. So perfect squares, we're going to talk a little bit about it, is just a number, right, times itself, or if it's squared, then the number that comes out is called a perfect square. So the number 1 is a perfect square because 1 times 1 is 1. 4 is a perfect square because 2 times 2 is 4. 9 is a perfect square because 3 times 3 is 9. So anytime we take a whole number and we multiply it by itself or we square it, it creates what we call a perfect square. Okay, now these perfect square numbers are going to be helpful when we're going backwards because if we can identify what we call a difference of squares, so they deal with these perfect square numbers, when you can recognize these numbers, then we can factor them rather quickly. So 1, 4, 9, 16, right? 25, 36, 49, 64, 81, 100, 121, and 144. Those are ones that we should know. And then other common ones are 13 squared is 169. 14 squared is 196, so very similar there. 15 squared, 225. So those are the ones that we're going to go up to. For the most part, you could make a list of a couple others if you wanted to identify those. So today, first of all, is factoring a difference of squares. So what mathematical operation does the term difference imply? So difference, remember, is subtraction. So whenever you're looking for a difference of squares, that means it's two of these perfect square numbers subtracting. So what we want to do is we want to look for those perfect square numbers, right? And we talked about it, the perfect square values. They are a number that has a whole number square root, or in other words, is created by an integer squared. I guess I can write that down. A number that is the product Awesome. So we have those listed up at the top. Recall, so this is kind of where we went forward with these. You'll notice when we took something like x plus 5 times x minus 5, we went ahead and we FOILed that. We got x times x, and that ended up giving us x squared. Then we did x times negative 5, negative 5x. 5 times x was a positive 5x, and 5 times negative 5 is a negative 25. We noticed that every time these binomials were identical looking, but with the opposite signs, it made those middle terms add to 0 or cancel out. So we ended up with a binomial. This is the only time we ended up with a binomial instead of 3 terms after we FOILed. And you'll notice that every time, right, we have a binomial times a binomial that's identical with opposite signs, those middle terms cancel and we end up getting a binomial. So the binomial that you see here is what we call a difference of squares. Notice this 64, right? 64 is a perfect square. Its square root is 8. 9 is a perfect square. Its square root up here is 3. So we look for that subtraction sign, and again, this was what we would call a difference of squares. When we recognize it's a difference of squares, we can recognize that really it's just where the middle term added to 0, right? So we can take the square root of this guy, and we know he'll go at the front of each binomial factor, and then we can take the square root of this guy and know that his square root is the second piece of each binomial factor, and that they have to have opposite signs. So those are really what we're looking at. So there's the steps here if you need to be reminded. Step number 1, factor out a greatest common factor if possible. We always do that when we factor anything. Number 2, confirm that it's subtraction. So you need it to be subtraction, not addition. Notice that all the examples 1, 2, 3, 4, 5, 6, and 7 are all subtraction. Then the square root of the first term, right, gets to be the first term of the factor. The square root of the second term will be the last term of each factor. And then be sure that the factors have different signs. So let's work through a few of these. First of all, looking at number 1, we have x squared minus 25. Notice it's difference, it's subtraction. And the square root, oh, that's moving, I'm so sorry. The square root of x squared, right, is just x times x. So we can split that one up. And then the square root of 25 is 5 and 5. And if one of those is positive and one of them is negative, that's where that middle term would cancel. And again, you could go through and check your answer if you wanted. You'd get x squared, right, negative 5x. This is one that we looked at. Positive 5x and negative 25. Those middle terms would cancel, leaving you with x squared minus 25. So just pay attention when we see difference of squares. Again, it's a binomial, and so it's a little bit different. Number 2, again, we look for a greatest common factor. Notice that the first term has a z squared, right? The second term doesn't have any z's, so no common factor there. So instead, we see that it's a difference of perfect squares. 4 is a perfect square, and 1 is a perfect square, right? 1 times 1. So we take the square root of 4z squared. That would be like 2z times 2z, and they get to go in the front of each binomial factor. The square root of 1 is just 1, and then we make sure that one of them is positive and one of them is negative. Now, if you look at number 3, this one is obviously not in standard form. The h squared term is second, but with a difference of squares, it's not really going to matter. We're just going to break it apart anyway. You can move them if you'd like to, but because we know that we're just using the square root of 49, which is 7 and 7, and the square root of 16h squared would be like 14h times, sorry, not 14, 4h times 4h. We know that they're going to go in here and that they're going to have opposite signs. Okay. Number 4, if you look at this one, we ask again, is there a greatest common factor? So notice that 50 and 8 both divide by 2. Now 50 has x's, 8, that term does not have any x's, so we're just going to divide out a 2 from each piece, and remember the 2 gets to come out front. If I divide 50 by 2, I get 25, and you still have that x squared, and then negative 8 divided by 2 is negative 4. Notice now I have a difference of, and 25 is a perfect square, and so is 4. 25 square root is 5, and 4, the square root is 2, 2 times 2. So what we do is we leave that 2 out front, and then we break apart this difference of squares, just like we have been on examples 1, 2, and 3. So 25x squared, again, its square root would be 5x. So we put that in the front. The square root of 4 is 2, and we need one of them to be positive and one of them to be negative. Okay. Maybe stop the video and see if you can do 5, 6, and 7. I'll go ahead and do them so that you can check your answers. But again, I would stop and see if you can do them on your own, if those steps are making sense, and you can refer back to the steps if you need them. So again, on this one, square root of 36 is 6. X and x, we want one positive and one negative. It doesn't matter which one's positive or which one's negative, so if you wrote them in the other order, that's just fine. Again, we look for a greatest common factor. Nothing divides out of 9 and 16. And so we break this apart. The square root of 9n squared would be 3n and 3n. The square root of 16 is 4 and 4. One positive, one negative. Number 7, look for a greatest common factor. 18 and 98 are both divisible by 2. So if we divide this by 2, we end up getting 9 x squared minus 49. And then 9 has a nice square root, and 49 does too. It has a square root of 7. So we break this up into 3x and 3x, 7 and 7, and 1 is positive and 1 is negative. Okay, that's the biggest one that you're going to work with today. I am going to go through this next one, but what I want you to notice is this next pattern, it's a little bit more challenging to identify as you're factoring. But essentially, we're just saying that, remember when we had like x plus 5 squared, and we said that squared, right, you cannot just put it in like that. You have to say there's 2 of them. so that you could actually FOIL it out and multiply, and you'd have that middle term ends up being a trinomial. Well, notice here you've got perfect squares at the beginning and at the end of these ones, like 4x squared and 9. They do end up like breaking down very similar to a difference of squares. However, the middle term, it's trickier on these ones because you have to make sure the middle term is exactly double the product of the first term and the second term. So this one's a little bit more challenging, but if you can identify that pattern, then you do know that it's just going to break up and it'll be a plus b squared, and it'll be a minus b squared because there will be two of the same thing. But again, if you notice this bold thing right here, it says the result is a trinomial with squares on each end. If you don't recognize this pattern right off, no need to panic. These trinomials can be factored using the methods we've already discussed. Just recognize that your final answer can be written as binomial squared. So let's look at a couple of these. So example 5, again, this one we're already good at with factoring these, so I just want you to notice you can use the same method. We split up the n squared as n and n. We look at the last term 16 and we think about factors, and we know that because this sign is positive, that those need to be the same sign, and everything's positive on this one, so we're going to have positive, positive. We look at factors like 16 and 1, 4 and 4, 8 and 2, and we need them to add to the middle term of 8. So the first one, 16 plus 1 is 17, 4 plus 4 is 8. Excellent. That one, 8 plus 2 is 10. So we know that this is going to be 4 and 4. So again, because I have an n plus 4 and an n plus 4, I can leave it like that, or we can write it as n plus 4 quantity squared. Okay. Now number 7, again, we ask, is there a greatest common factor? Notice that all of these values can be divided by 9. So before I start trying to do bottoms up and multiplying that 9 to the back to get a huge number, we need to take out the factor of 9. So if I divide that by 9, I just get z squared plus 36 divided by 9 is 4, and there's a z there. And again, 36 divided by 9 is 4. So again, if I'm going to finish factoring this, I pull this apart. Now the z squared again is just z and z. Notice everything's positive in this one, so everything's going to be positive in the factors. And then again, I'm looking for factors of 4 because of this last number here that are going to add to the middle term. So that would be like 2 times 2. So I put 2 in here. Hopefully you can tell the difference between my z's and my 2's. Okay, same thing moving down. So factor the quadratic expression. Again, these are just ones we've already done, so we split up the d and the d. Oh, and I didn't even show you. Sorry about that. Up here on this one, let's go back just a little bit. Again, you could write this because it's z plus 2 and z plus 2. We could write 9 z plus 2 quantity squared. Okay, back to 8. Again, let's split this up, d and d. Notice this guy's positive, so we do want them to be the same sign, but everything has to be negative. So factors of 25 would be like negative 5 and negative 5 to give us the negative 10. So we could write this as d minus 5 quantity squared. On this last one, you'll notice that there's not a greatest common factor. So 4 and 12 and 9, nothing divides nicely into those. So this is one where we start bottoms up. Again, if we are struggling more with the pattern, so we just go x squared minus 12x plus 4 times 9, which is 36. We go ahead and factor. Again, we know that we're looking for factors of 36, and it looks like they're both going to be negative. And we want them to add to 12. So we're thinking, let's see, I guess we can just list them, 2 and 18, that adds to 20. Negative 3 and negative 12, nope. Negative 9 and negative 4 adds to 13. Let's see, what else is it divisible by? Negative 6 and negative 6. Ah, excellent. Negative 6, negative 6. We get x. Oh, then we got to finish bottoms up, right? I about forgot. So finishing bottoms up, we've got to multiply the 4 back out. And when we do that, 6 over 4, that's really like 3 halves, right? If I simplify that fraction. And then we go bottoms up, so we move that 2 up there. So 2x minus 3 and 2x minus 3. Again, you can stop there, or we could write that as 2x minus 3 squared. Perfect. Okay, let's look at an application really quickly. Just some introduction to applying these properties. So if you look at this one, it says a bird picks up a golf ball and drops it while flying. The function y equals 81 minus 16t squared, so here's our function, represents the height in feet of the golf ball t seconds after it's dropped. The ball hits the top of a 32-foot tall pine tree. After how many seconds does the ball hit the tree? So first, understanding the problem. Well, they gave us a function, right? And we just need to understand kind of what it means. Why they said represents, this is feet. Oops. And this is height. So height in feet. And we're assuming that's above the ground. So notice if I wanted to look at, well, how high is it before he drops it at all? If t represents time in seconds and say t was 0, right, that makes this whole thing go away. It looks like he's 81 feet in the air when he decides to drop that golf ball. Again, t is time in seconds. Okay, so every value we put in for t, we could figure out how the height is changing. It asks us how many seconds or after how many seconds, so we know we're going to be solving for t. Does the ball hit the tree? So you're going to solve for t. That's the first thing we want to recognize. When, right, it hits the tree. And the tree, it told us, is 32 feet tall. Oh, just scribbled that out. So when y, because y is the height, the ball hits 32 feet, right? So when y is 32. So all we do is take our equation. We put 32 in where the y was. Got 81 minus 16t squared, and then we solve. Now remember, when you solve, you need to set the equation equal to 0 first. So we're going to move this 32 over to this side, and that ends up giving us 0 on the left side of the equation. We go 81 subtract 32, and that gives us 49. And then we have minus 16t squared. Now notice this is a difference of squares, so this is one I'm going to use the difference of squares pattern. I've got 49 subtracting, right, 16t squared. So on this one, the square root of 49 is 7, so I know that's going to be 7 and 7. The square root of 16t squared is 4t. And it looks like I'm going to have a negative, right, and a positive. Now with quadratics, you're often going to get positive and negative answers, and one of them will work because you can't have a negative time value on this scenario here. So we just need to state the solutions. So remember, we ask what value of t would make this piece be 0, and again, if you're stuck, you just set that piece equal to 0. That would be like subtracting the 7 over negative 4t equals negative 7. If I divide by that negative 4, that means that t is equal to a positive 7/4. Now you can do the same thing with the second piece, right? Take 7 plus 4t and set it equal to 0. You'll get 4t equals negative 7, and then divide by 4. So your two solutions here is either t is negative 7/4 or t is 7/4. And again, it can't be a negative value because we're talking time. So we're going to ignore that solution. It's not valid. So we know, right, that the ball hits the tree 7/4, or in other words 1.75 seconds after the bird drops it. Okay? So there's kind of an application with the difference of squares. Again, you're going to, on your assignment, practice. Some will be difference of squares. Some will be binomials with just a greatest common factor. Some you'll need to use the bottoms-up method. Just make sure that you're always looking for a greatest common factor first. You could even go through and do the whole worksheet where you just pull out the greatest common factor. Once you've done that, then you're going to continue to factor if you can. And then you're going to take a quiz that will have some of these factoring pieces on it.